Well, thank you for joining today for this webinar on the analysis of the available information that we have for the April 28th blackout in the Iberian Peninsula. This is a collaborative work across many of my colleagues and myself at the Grid Planning and Analysis Center at NREL. So let's get to it. Let's first start with some of the preliminaries about the blackout. They have some figures. At this time, we already have reports about what happened, and we saw since the event until today, we have seen several opinions and several ideas about what could have happened in Spain to that period. And in today's presentation, we want to talk about some facts, some informed opinions. We label them adequately because we don't have as much information as probably the operator in Spain or the European operator, but we do have a ton of data that we've collected for this effort. Data that, for example, we have frequency data that spans all the way to Riga in Latvia, to voltage measurements close to the Iberian Peninsula provided by our collaborators in the INESC in Brazil and Porto. And we also know that, that there's several locations where some of the original trips started. So we're going to go ahead and start presenting some of these findings and some of these analyses that we have. First of all, let's take a wide view of the different timeline of the event. So these changes that you see here, we've actually highlighted where the market intervals happen. So you can see when you see changes in the frequency, like in this plot, we can identify when there are contingencies and when there are actually like events of the market. So here we can see that around noon, from the data that we have a first oscillation that happened. Then there was a second oscillation, and shortly after, several of the contingencies started to go through. So, most of the event has focused on this gray window at the end when the actual blackout started. And we can see from this situation that we have a window of time where there's a certain oscillation that happens locally, certain oscillation that happens which more regionally through Europe, and then finally the complete blackout. If we take a look at the voltage measurements for the same period, we can see here that we have a measurement of the first oscillation going on, which mostly affected locally Iberia. So you can see a measurement of voltage around Milan, where these oscillations did not actually make it through on the voltage across continental Europe. We can see the big oscillation that happened first in terms of magnitude and a smaller one in terms of magnitude and voltage. So basically the conversation today is about how did this come to happen, and like what can we learn from this event about power system operations with large penetrations of inverter-based generation. So the timeline that we have is we have an event between 1203 and 1207. That is a first oscillation around 0.6 hertz. Second oscillation between 1219 and 1221. And by the time that we actually put together this slide the first time, we had a hypothesis that there were certain things that happened in between the oscillations on those 12 minutes before the first generation trip and the second oscillation ending, where one of the hypotheses was that there were likely several operations taken by the operator in the grid to try to dampen those oscillations, and that those operations conducted by the operator could have had effects that drove the first generation trip. So now that we actually have the full report, we can discuss what those operations were. So what were the operational situation in Spain? Generally, the data that we have is, by the time that the event happened here in this red window, the penetration of renewables in general, like with respect to the total load, taking into account the load produced by the hydro pump, was about 75%. And as you can see from the days prior to this day of the blackout, and even some days afterwards, we can actually see that this level of penetration of renewables is not something abnormal. So Spain had operated with similar shares of variable renewable generation during that blackout and days prior to the event, right? And the total participation was similar through the month of April. The inertia, which was one of the first culprits that was discussed in the original conversation, was around, now is known to be around 2.3 seconds, which is higher than the 2-second floor set by the European operator. So we obtained this data to basically start explaining that the situation that was on their operations that was conducted in Spain as a share of solar and wind was actually not abnormal. The operator had plenty of experience and plenty of operational windows that matched the type of integration that we saw for the day of the blackout. Actually, you can see here in the plot, in the stack plot of the fuel, that the day prior was very similar to how the day of the blackout happened around the same time. It's very actually even hard to tell if there are significant differences between one of the stack plots and the next one. Then in terms of the exports and imports, Spain was producing a lot of power and it was exporting into France to the interconnection lines. We can see here again through the month of April that the shares of exports to France were not actually out of normal either. They were actually not the highest one either from previous days. So again, one of the original hypotheses that was like floating around was whether these oscillations could actually be similar to the ones experienced in 2016, when there was a high export amount into France and the oscillations were observed. But again, like if we actually look at the data, we can see that through the month of April, there was nothing abnormal. There was no, high amount of exports beyond the expected for the Spanish system into continental Europe. Now, one of the interesting pieces is that, or one of the things that was discussed, like, well, even though the blackout happened around the noontime, heavy fluctuations of voltage were observed in the Spanish system. So this was a screenshot from a power quality measurement taken in a wind power plant in this location in Spain, where we can actually observe just very high, up to 11% voltage fluctuations even 2 hours before the event started. Now, originally, this was one of the speculations that were tossed around. Now we actually have confirmed it, like given the data and the measurements obtained from the official reports, these oscillations of voltage, these fluctuations were actually confirmed that they happened, right? So we can see now, like, again, this was some of the original screenshots that were shared. And now we can actually see from the official report of the Spanish operator, this same pattern of fluctuations across the system. So again, if you see the timestamps in the report, you can see that there were heavy variations in the voltage starting all the way back to 10:30 in the morning. So that what we can observe here is that even though the focus of the study and the focus of the conversation around this blackout was close to the time that the oscillations happened, voltage problems were going on already in the system like several hours before the actual event. This is another plot that was part of the ENSOE publication, where you can actually see again, and closer to the times of the blackout, really high voltages happening in the system, right? Here you can see voltages in several regions across Europe that were actually reaching heavy variations of voltage. So this is important because, again, one of the first hypotheses driven by the power systems community about the blackout was very focused on issues of inertia. And what we're observing here is that now that we have the data, the system was already experiencing heavy voltage problems way before the oscillation started to happen. And the reason I want to focus on the oscillations of voltage is because the first actual now within the window of analysis of the data that has been made available, we can actually start looking at the first oscillation, which has a 0.6 hertz frequency. And this is actually not oscillating very heavily against the rest of Europe. You can see that the participation of the other, especially the Latvia participation with respect to the local Iberian one, is actually relatively small. And these oscillations are in phase between Spain and Portugal. The report of the operator now has identified that some power plant, not actually identified the actual name, but the controls were causing some of this oscillation and was having this like a feedback loop. And the interesting part about this oscillation being driven by a control in a power plant is that the system was already having voltage problems. So there is a question about how much of the controls of those power plants actually were, they could support these kind of oscillations in the system where they're taking measurements for the control. So the first oscillation, again, is a local oscillation in Iberia, a system that is already going through heavy variations of voltage across the system. And one of the power plants starts to latch on of these oscillations and create a feedback loop. And then we see like some mild like correlation with the rest of Europe. So the first oscillation gets dampened down, but here you can see again on the voltage side, right, in Faro and Portugal, these heavy voltage oscillations actually being observed as well. And the reason again I want to focus on the voltage is because although we have this oscillation and the report now actually connects this to one of the power plants, the voltage in the system was also varying quite a bit, right? And again, we want to thank some of our collaborators of the INES in Brazil to provide some of this data that is not necessarily one of the publicly available, but we can see this relationship now where the voltage, particularly in the Iberian Peninsula, was already experiencing problems. The second oscillation happens a few minutes later, then this oscillation has a significantly different signature. Here, now we can see that this oscillation actually is against the rest of the European system. It has a signature of around 0.22 hertz. And now we can actually observe the rest of the European system oscillating, not only locally for Malaga and for Porto, but also against other nodes and so far away as in Latvia, but also in Switzerland, in Germany, and in France. And this is the interesting one because now this oscillation is in phase. It's 180 degrees out of phase with the rest of Europe. This oscillation now has the same signature and is very similar to the one observed in 2016. So again, now we have an oscillation that looks more familiar to the operator. Like the first one looks more localized, more regional. This one actually is with the rest of Europe. And here we can see actually the voltage signature again. And here we can actually see, for example, on the frequency side and on the voltage, that this frequency is also observed. Again, this is the 180-degree difference between the oscillations happening local to Europe and, for example, against Milan. Right, so the operator started reducing exports and attempting to bring other synchronous generations online. And the reason for this is because there was a protocol from the 2016 oscillation that said, if you do these kind of operations, reducing your exports and changing your operations, you can actually dampen down this oscillation that was observed before. And as we're going to learn, like an operator in real life actually has very little, discretion about what to do to reduce this oscillation. They generally follow a protocol. So the question that we had was, after this oscillation happened in those 12 minutes, what were the actions that were taken that could have actually driven some of these situations? And again, we will look at the changes in the interconnection, right? As I mentioned, in the 2016 event, the operator actually reduced the interconnections. This is from the 2016 report, where and then in 2016 was brought from 20 to 50 megawatts to 1,000 megawatts to restore to essentially reduce that. And in April 28th, the interconnection flow gates get reduced to 1,500 to 1,800 to alleviate these oscillations. So what we can see here is that we have a picture of a timeline where there's heavy voltage fluctuations in the system. We have a first oscillation from a power plant latching onto these oscillations and gets dampened down. Then we have a different oscillation that have a different nature, where we have something that is actually happening across Europe, and the operator taking actions according to its protocols to reduce that second oscillation. Right, and then this is again the interconnection changes. This plot here is from the data from the operator, and this is actually a far more detailed plot provided by the reports of the Red Electrica, where you can see here these reductions in the megawatt flows, right? So the thing that wasn't clear, and I think that is still under study, is that we know now which were the interactions between the transmission maneuvers done on the operator, but we don't understand if those who actually interacted as well with the market operations, right? Because some of these maneuvers were happening while the market was changing and some units were coming in line and out of line. So 12 minutes before the oscillation of the generation trip, now we have this voltage data, which we didn't have. The community didn't have this data prior, like when the event first happened. And here's where you can actually see that as soon as the operator starts taking these maneuvers, the voltage starts to rise, and it starts to rise, and it starts to rise quite significantly. And the frequency also starts kind of staying still. And then at some point, we have this dropping the frequency, where this is the market, actually the market action, but the voltage is already pretty high in the regions of Faro and Porto, right? So the operators realized that they need to start bringing the voltage under control. And in the report, it actually says that the fastest thermal generator they could actually bring online to provide voltage control was a 90-minute startup. So they could actually get it online before 2 in the afternoon. In this process, under these 12 minutes, the operator connected 5 induction shunts to try to bring the voltage down. They closed and opened circuits. So if you go through the report, there's several pages of all of these maneuvers the operator was taking to try to control the voltage that was already rising. So again, like the interesting phenomena here is after the oscillations happen, there stands to reason that some of these protocols that the operator followed to try to control the oscillation just creating a voltage runoff problems. And the operator closed more circuits to try to control the oscillation, which is kind of what you learn in your power systems class. The oscillations are created by a weak grid, so you close more circuits, you create this grid strength, but it just worsens your voltage rising problems. And then the first trip happens, right? And we can see here that this is like a pretty aggressive dip in the frequency. And as soon as the first generation falls, then we, like, according to the report, it was around a 317 megawatt generation, and that included distributed generation is more than 1 megawatt. So the interesting phenomena here is that this is not just a frequency event, but the voltage things are happening. And you can see here from the Rokoff, the rate of change of frequency, that at no moment the rate of change of frequency was even close to trigger rate of change of frequency protections in the system. And one of the things that we observe in this plot for the first seconds after the blackout, after the trip, is that we don't observe any visible response from the reserves. There's no data in the report so far to explain like this downward behavior of the frequency, despite the fact that, again, if you look at the rate of change, the frequency itself, the protections for frequency are not within the range that could have actually triggered a trip of more units due to frequency changes. And again, I want to point that out, like as a community, we first figured out that the rate of change of frequency was too high, but we realized here that it wasn't, right? But yet the frequency started to drop. So in this particular window of time, the maximum tolerance of, depending on how you measure the rate of frequency, is 0.2 hertz or 0.05 hertz, which is pretty far away from the European regulation for actually tripping units due to rate of change of frequency. So if we actually observe here the voltage, we can actually see again that the voltage in Faro, which is one of the closest measurements to the southwest of Spain, was already pretty high, right? And we have here a drop in the voltage, but you can see here that the voltages in that region were like at pretty high levels. And this is not necessarily close to where the power plant stripped, but it was already like a big problem. So we have this loss of generation in Granada, and we can see the measurements in these other locations follow the same pattern, right? So the other part that, again, it becomes interesting to the context of voltage is that in the report, it says very clear that the G-1 generation 3, the very first one, was a unit producing 355 megawatts, but it was consuming 165 MVAR or reactive power. So this is important because if you have an overvoltage problem already, and the plants that are tripping were actually consuming reactive power, were providing regulation downwards of voltage, that just worsens your voltage problem. In the second phase of the event, you can see here the loss of the N-2 and N-3 that happen very close to each other. Again, the frequency delta, the rate of change of frequencies is higher than the previous window, but it's still not large enough to trigger rate of change of frequency protections. Right? Again, if there's no visible response so far after this happened of the system trying to recover the frequency. So again, the deltas here for frequency don't explain really why there could be like a lack of response to try to bring the system back from the active power perspective and the frequency. And then this is where the plots start to get really interesting, because the data showed us that after this second loss of generation in Badajoz, the voltage starts to rise, and the operator starts to, you see this voltage rise, then we lost a second unit again in Badajoz, and the voltages continue to rise, the frequency continues to drop, and at some point we actually lose the generation of the 6 trips that happened, right? There's an extra generation loss here, and we could continue to see the voltages continue to creep up and the frequency to drop. So at this point, there's a reversal of the flow with France, where the system in Spain continues to trigger voltage trips, and the loss of power generation reverses the import to export, right? Sorry, the export to import. And then finally, in the last stage, close to the blackout, here is where now actually see that the line between France and Spain trips. Now that's kind of like the dead knell of the Iberian system, where now we can see this rapid decrease in frequency. The overhead lines between Spain and France get disconnected, and now we actually see the rates of change of frequency that could explain this connection of more units. And one of the other pieces that happens here is that due to the under frequency load sharing protections in the Spanish during the Spanish system, because it's protecting against this loss of frequency, it probably worsens more the speed of change at which the frequency drops, because you're losing all of this huge degeneration that was operating at the time. And again, in this last bit of time, here's a little bit of like where we left off in the last trip. And you can see here the voltages continue to creep up. They come down a little bit and then continue to go really high. And this is due to the trip of the hydro pump storage. Again, the hydro was consuming active power, but it was injecting reactive power. And due to the under frequency load shedding, then you lose also that capacity to absorb reactive power in the system. And by that time, all of the 6 stages of the frequency load shedding happen. You lose the pump hydro, the voltages get completely out of reasonable operating values, and the system blacks out. Now, one of the main lessons that we get from this is that we as a community power system, we have been waiting for something like this to happen to explain how we've been talking about inertia for so many years. For many, many years, we've been waiting to talk about inertia as one of the issues that could happen if you have this kind of high penetration of inverter-based generation systems. However, the reality that we can observe from the data, what the data tells us is that this is more of a voltage problem than a frequency problem, than an inertia problem. And this is a very uncommon set of events for a power system engineer to see. Because a power system engineer, you actually learn that when the system is overloaded, voltage and frequency drop together. And when you're trying to stop a blackout or a cascading event, those two things can happen at the same time, right? We talk about voltage collapse, we talk about system collapse. And this behavior is actually pretty uncommon. And I think that in the last IEEE general meeting, Professor Kostas Bournas was the one who said that this was observed once in an island in Greece, but it's very uncommon. Like I looked into blackout reports for many, many decades, and I couldn't actually find signatures of blackouts that look like this, where you have rising voltages and dropping frequency, right? This kind of goes in two opposite directions. And this behavior is explained by the fact that a lot of the generation that was synchronous generation in Spain was under-excited at the time of the event, but it was also providing active power. So as the voltage starts to rise and trips because of voltage reasons those units, you're losing the active power, but as the units trip, you have a run of voltage going upwards. And again, this plot is from the data that we produce thanks to the INES data. And then this is the detailed ENSOE publication that confirms for other several locations in the region, the same problem, right? You have, maybe you cannot see well the timestamp, but this starts around 12:30. You can see the voltages go down and then suddenly start tripping up until we have this runoff of over voltage that led to the blackout, right? So again, let's do a quick review of what we've learned so far. The system was experiencing high voltage fluctuations and oscillations. We have an oscillation of a plant that latches onto this voltage fluctuation. Then we have an oscillation with the rest of Europe. The operator tries to dampen that oscillation following protocols. Those protocols just worsen up a voltage situation that was happening hours before the blackout. And then we have a runoff of voltage that starts tripping units and losing frequency and increasing even more the voltage. So again, in the last few seconds before the blackout, you can actually see this rise of voltage. I'm zooming in here. And this behavior actually, again, makes things worse because as you're on the frequency load shedding, it starts to act, you're just making worse the voltage problem. Now, this behavior actually in the US is a known risk, although it's not actually explicitly regulated. So the only mention about this kind of problem, again, just to emphasize how uncommon it is that the NERC PRC 006 just says, when you're tuning your under frequency load shedding, just be careful for over voltages. But it's not actually properly regulated, right? It's just a known risk. But this brings a question about when you operate a system with this high level of penetration of inverter-based sources that don't actually regulate voltage, that don't actually regulate reactive power, what should be the interaction between those controls at the plant level that is regulated to power to be a power factor of 1 and the rest of your system protections? Now, the question about inertia keeps popping up about this event. And I want to emphasize that I think that the community has been looking for an event like this to talk about inertia because we've done so much research on it. However, if we actually go back in time in Spain, in January 9th of 2025, the same year, there was a huge generation trip during a high penetration of wind in Spain. The wind was providing about 70% of the load that, in Spain, about 2:30 in the morning, Central European time, and 1 gigawatt loss of generation happened with the loss of the nuclear power plant. And you can see here from the data that we collected for the frequency during that event, that the frequency barely moved, that the rate of change of frequency barely changed. So again, it is not a matter of whether frequency alone and renewable energy penetration or inverter-based generation could be the culprit of an issue related to a runoff of frequency, because the Spanish system has already operated and survived events with similar amounts of renewables and similar amounts of inverter-based generation in the system. So that, and the interesting thing is, like in the report about the nuclear power plant trip, it was an under-excitation protection that tripped the unit, which meant that the system was already under a heavy under-excitation trying to control the voltage and not the frequency. And the reason I bring this up is because under-excitation in a synchronous generator weakens the electromagnetic field of that machine. Actually, we look at this, what is called the capability curve. You can see that the stable region when the machine is overexcited, means providing reactive power, is way larger than when the system is not providing reactive power and it's actually consuming and it's underexcited. So if the coupling becomes too weak between the generator and its electromagnetic field, the synchronism is hard to maintain, especially under low load or during system disturbances. So again, let's look back into what the operator was doing. It was basically saying, I'm going to bring up more synchronous generators. I'm going to bring up more gas power plants and bring up my pump hydro to regulate voltage. But I'm going to have to because I have so much renewables in the system that are not set up to regulate, those units are going to start regulating voltage under excitation and also at very low levels of loading, which just worsens the situation of the electromagnetic stability of the machines. And in Kundur's book, like one of the classic power systems books, it says very clearly that under-excited operation of synchronous generations increases their susceptibility to these oscillations in the range of 0.1 to 2 hertz. And what was the second oscillation that we saw in the system? It was 0.22 hertz. It's almost like a textbook case of a system that has not required renewable generation to actually provide voltage regulation and is relying on synchronous machines, forcing them to operate at a risk of causing oscillations and increasing the susceptibility to adverse effects of under-excitation on the damping torque. And we saw that already happening in the previous slide, that in January, when the nuclear power plant tripped, it was because it was operating in an under-excited regime. So we still have like some open questions about the event. The oscillations at the end of the day play a role in the generation trips. I don't think that the reports clearly are able to distinguish that. I think that that's a massive question. So it's going to take time before we understand if the oscillations themselves play a role in the generation trip. We just know that the trip happened at a particular time We know the voltage was high, but we don't know exactly the details of why that machine tripped. For that, we require data on the actual controls of that machine, knowing which flag was the protection, which flag was used. Can the misoperation of reactive power control cause to mitigate the oscillation lead to the first generation trips? We also don't know this. Again, the operator was following the protocol of connecting more lines and connecting the STATCOMs to try to bring down the voltage. Again, changing the balance of reactive power through the system. We still don't know if that could have actually led to this first trip. And then the question is, what role did the generation control settings play? Like, were the generation controls, especially around the renewable power plants, actually worsen the situation? And is the addition of grid enhancing technologies can avoid these issues, right? So we don't know about this because we need to understand better at the plant level for every one of the trips what the flags were. Some of the takeaways of the available data is that the system was operating within normal conditions in terms of this renewable penetration and exports. Like, it wasn't exporting more than normal, it wasn't producing more than normal. There's 3 loss of generation events and a complete disconnection from Europe in 20 seconds. It is no surprise that a system that has to go through these N-3 contingencies plus islanding goes into a blackout. In 20 seconds, an operator cannot actually have maneuvers to bring the system, to save the system from collapsing. Can we blame low inertia? Well, the data that we have now shows that it's extremely unlikely that it's low inertia. Because it's true that after the disconnection of the inertia, even though the inertia was low, the system was able also to recover from the Almaraz event with no problems on the inertia side. And one of the things that we know now is that voltage problems in the Spanish grid were driven by this inadequate reactive power generation control, right? And then we have this uncommon set of situations that led to the collapse. So we have increasing voltages, decreasing frequency. We have generators in the system that are not regulating voltage due to the grid codes. And these overvoltage problems actually were known. In July 2022, the operator proposed a demonstration to pay for these services. Right? In Spain, the regulation is that the power plants need to operate between 0.98 and 98 power factor, which essentially makes them behave like a negative load. And I think that this is important because a lot of the conversation has been about what is the primary energy source behind these generators. And what the data shows us is that if you actually had put any source of power, but you force those generators to operate within such a narrow power factor window, the physics of power system transmission and the lack of loading of the transmission lines, the excess reactive power, would have caused the same type of event. The other interesting thing is that early this year, we had a blackout in February 2025 that had a similar sequence of events. Northern Chile was exporting right amount of power into the middle of Chile. Then as a line trips while there's high voltages. And then the moment that we lost this line and there's high voltages, then there's a sequence of events that create over voltages in the north side. And once the system is split in half, eventually it collapsed, right? So we're observing that in many ways, the way that renewable power plants and inverter-based resources have been made operate with limited regulation and participation of reactive power control under low loading conditions, then we're creating a new version of what a stress scenario looks like in the system. So when I was an undergrad and I was studying like high stress events on a power system, we used to study the situations of like heavy load, and we would conduct these exercises of increasing the load in the system and figuring out if we could maintain voltage and the voltage were low and you have these problems. Now, integrating significant amounts of inverter-based generation that is not providing reactive power control under loading conditions means that we have to start rethinking which scenarios we study when we make this integration analysis, and whether gathering new data about these stress scenarios could reduce the probability of major events. Because the situation that we observe is, in most likely, the rules of the grid code to integrate inverter-based generation that doesn't provide reactive power control is fine if you go to, like, let's say 20-30%, but now reaching 70% of penetration with the same rules. It stands to reason that the system started to suffer from conditions that made it unstable. So can this happen in the US? Well, let's start to look into it. Like, one of the closest regions that has the similar amount of penetration is California. Southern California, Northern California, you have this split similar to Europe, where you have high inverter-based generation in the south with high hydro in the northern part. We have a situation where for 56 straight days, 100% of the renewable energy were more than provided a lot of this energy in the system. But California, again, has a large amount of storage systems that provide regulation of reactive power. And right now, we actually, by May 20th of 2025, there were up to 10 gigawatts of storage that actually were dispatched in the California system. The other aspect is that California, the largest system in the WEC, which is the whole western of the US, and is likely to experience the kind of oscillation over voltages. But this is a well-studied grid that suffers from some of these oscillations, and several activities have been conducted to be able to dampen those. So the reality, California seems to be a low risk and very low likelihood of an event like this happening, given the grid code and the amount of storage that is in that system. The other system that has large amounts of renewables in the US is Texas, right? Texas operates with approximately 50% share of renewables. Inverters can make up to in the code of Texas, inverters with gross rating more than 20 MVA have to provide voltage support according to the IEEE 2800. So the Texas has a substantial share of energy storage, and every single inverter-based unit, whether it's solar or wind or storage, has to provide this control of voltage. So Texas has this huge amount of resources converted to inverters, but different than Spain, it actually forces them to provide voltage support, which was not the case in Spain. So the lesson that we get from this is we have been discussing for many decades the issues of potentially low inertia systems. In many ways, I think that that's because that was kind of one of the identified risks from the simulations that were conducted using transient stability tools that were very focused on stability for active power and frequency and rotor angle stability. And what we're observing by two events in this year, one in Chile and the one in Spain, is that voltage is actually coming to bite us first than the inertia problems that we predicted. And at the end of the day, one of the biggest risks that happened in the Spanish and the Iberian system was operating the system at such high penetration of any source of generation without the requirement of providing the active power control or voltage control. So thank you very much. And I think we're going to take some questions now.
Wonderful. Yes. Thank you for your presentation. We do have 20 minutes before we dive into questions. Are there any other sections that you wanted to add anything else or anything else you wanted to cover?
We can go to the questions now.
Perfect. All right. First question. Would grid forming inverters have helped prevent this event?
I mean, probably they could have been aid if they actually were given the bandwidth to provide voltage control. So grid forming inverter on its own doesn't really provide more better or more control than grid following, but you could also just have your grid following inverters provide regulation of the voltage, and in that way prevent it. So even though grid forming is being touted as a technology that will help integrate more inverter source generation, in this particular context, what we see from the data is that it could have helped, but it wasn't the silver bullet, right? It needed to have this capability to regulate voltage. And grid forming, in many ways, is a technology to try to regulate frequency and variation of the active power as well. So we need probably to do more research to see if grid forming could have actually alleviated this. But what we can see from the data is that even if it's grid forming and grid following, the big challenge was where the existing technologies already present in the system required to provide this voltage control for the grid.
Wonderful. Thank you. Next is, could other resources have helped the situation?
And I want to mention this, a lot of the focus of the public conversation has been around the topic of renewables versus non-renewables versus gas or nuclear. And in fact, as we saw from the slide here, if you have had any type of resource on the other side of your energy conversion technology have operated under such a small range of voltage regulation, you would have triggered the same kind of problems because the existing synchronous generators in the system were already underexcited. So whether it was renewable or not, or nuclear or not, is more about what are you asking these resources to do, and what are you asking them to do in terms of supporting the voltage of the grid, and less about the primary energy source on the other side.
Thank you. The next question is whether what other options is Spain considering to prevent this in the future?
So actually, Spain, like as far as I can tell, tried to pass a law that was rejected in the Congress, where they were trying to revive these programs to pay for reactive power in the existing renewable, in the system, existing solars and so on, and kind of reform some of the aspects of their control requirements for these type of resources to prevent issues like this, and also, you know, increase some of the interconnection to France and so on. So the easiest thing that Spain can do is essentially make these inverter-based resources provide voltage regulation. That's actually, like, let's call it like from the capital expenditure perspective, that's probably the cheapest option. The second thing would be actually to increase the penetration of storage, right? As we mentioned, and there's certain conversations that we're having where, okay, we should have synchronous converters or some other, or these kind of classical synchronous machine devices. But again, if the system is experiencing over voltages, a lot of these synchronous condensers don't help as much as batteries, because batteries can actually operate across this whole circle of control to consume reactive power and active power. So, you know, if you were to do capital expenditures to try to support the increase of new technologies, again, this new law that was trying to be passed was trying to incentivize, again, this like installation of new batteries and so on. So probably you don't really need to have a really high capital expenditure to fix part of this problem. And if you just incentivize the installation of new batteries from private, you can actually solve a lot of these issues, as long as you ask those batteries to provide voltage support. So, you know, again, a lot of conversations I've been having in the public context about, like, should they invest in this technology, that technology, the other? Better regulation and storage that can actually provide support would be like the closest and cheapest solutions.
Thank you. The remaining questions are a little longer and technical, and I feel like they're better read from your eyes directly. So I think you want to take a moment to scan the
Yes,
one.
1 second to stop my screen share.
Of course.
I'm going to read some of the questions. Let's see. Q&A. Here we go. There seems to be several timelines from LT planning to real time, in particular, as noted in the NESO report this week. Best practice for a system facing more voltage volatilities to schedule generation day ahead that could be used to counter raising voltage. Well, I mean, like, actually, the Spanish operator, to answer Michael Hogan's question, they had scheduled some units to provide this, and the day before, that unit actually couldn't come because of a unplanned maintenance. So unfortunately, the unit that was scheduled to provide some of this support was not available. And again, once they start observing these issues with the voltage, they try to bring another unit online, but it will take 90 minutes to come in. So again, I want to come back to my previous answer, where, like, if you actually use storage and more inverter-based generation, you can exploit the capacity of inverter-based generation to quickly answer to these changes in voltage. So although there's a benefit of scheduling and trying to study the system moving forward from the day ahead, I think that in many ways, having the right technologies in the system to provide that support, it's also relevant, right? And again, I think that the Spanish operator had within their protocols bring this extra unit online that just didn't come as expected, right? Then there's a question from Jim Lazar about the DG tripped. The reports don't have too much information about the DG tripped, unfortunately. They just says that the distributed generation trip, there has not even any information so far about whether those DG were tripped because of high voltage, like high voltage on the distribution side that came from the transmission side that could have tripped a protection for high voltage, or they could have tripped for other reasons. Now, the hypothesis would be, given the sensitivity and the IEEE 1547 requirements, the most informed opinion about it is that the likelihood is that they also trip for high voltage situations. There's an anonymous question about the impact of high wind and solar generation. I don't think that, again, I think that the original hypothesis in many ways were around whether solar and wind, and the reason that they're variable generation and they have this idea of they change because of the weather could be the culprit. But as I was mentioning, the data that we have shows you it doesn't really matter what primary energy source you were using. Is if you were not regulating voltage, you would run into the same problems that happen. So I don't think that there have been any changes significantly to the policy in terms of like how does the market operate and how to dispatch solar and wind. There are several types of generation. This is from Andrew Thompson. Yes, so Andrew, you're right. Like, there's a lot of things happening, right? Like, the question was, are these voltage issues that you were observing 2 hours before the blackout driven by the lack of regulation of some of these resources that the renewables were not generating? Then when the over voltages are happening all over the system, as you know, voltage is a local problem. So there could have been trips of synchronous generators that were conducting that reactive power consumption, as well as renewable generators as well. And then once the voltage gets out of whack and you start losing both all types of generation, all types of resources, then the system just kind of goes on these runaway voltage problems, right? So that when I was mentioning the fixed power factor requirement, it was because that's how you get to the condition where the voltages are rising out of control. And then whatever order things trip, once they start tripping, there's no way to say, oh, because this tripped first and the second thing tripped second and so on. That was the reason, right? From Michael Hogan about the pump hydro, it was tripped because normally there's an under frequency load sharing trip for this. Like, there's a protection scheme that the first thing that trips on the low frequency condition, according to the Spanish regulation, and what it was actually mentioned in the report, that's kind of like how this protection scheme is set. If you have a frequency loss, the first thing to trip is the pump storage, and then you lose load, right? So the reason for this is like if you actually stop pumping water from the pump storage, that's a less dramatic for society loss of consumption than if you actually trip houses and industries and so on. Arjun, you're actually here about the synchronous condenser and generation. I don't think that Spain has synchronous condensers. I didn't see anything. But as I mentioned, a lot of people were expecting that the synchronous generators will continue to maintain this voltage regulation. But if the voltages are running out of control, you also want to trip them. And as much as you trip them, you essentially lose this reactive power consumption. Many have, and from Michael Hogan again, many have responded that part of the solution is to require VRs to operate in dynamic power factor mode, and this is the case. I mean, I think that, again, to Michael's point, is like, there's the 2800 regulations, there's certain grid codes that tell you that if you allow this, there's different ways of conducting reactive power control. These studies are conducted by the operators who know the system better. I don't work in the operator, so I don't know which strategy for voltage control is the optimal to have put in Spain. And so you don't create interactions between the different energy sources trying to control things at the same time, and several very technical challenges that when you require inverter-based resources to voltage controls the system. All we can tell from the data that we have is that more reactive power control and voltage control was needed for the system to avoid these runaway voltage problems. And I cannot really answer what will be the ideal. There's pretty talented engineers in both in Great Britain and ERCOT and CAISO that come up with these regulations and run significant amount of simulations to figure that out. From Andrew, yes, you're right. That's 0.2 hertz. The 0.2 hertz oscillation is a well-known one. I think that there are multiple reasons why that oscillation was dampened in a way it was. If you look at the report from 2016, there's both the dampening the dampening controls set up. But again, I want to come back to my slide about if you have all of these generators operating at really under excitation, that condition, probably whatever additional dampening was coming from the control was insufficient to handle the lack of the loss of synchronous of torque, of dampening torque in the machines that existed in the system. So the conditions that happened in 2016, from what we can see in the reports, were different from the voltage perspective and the operating point of the units than the one in 2025. So I wonder if some of those controls needed to need to be updated to handle out these new operating conditions. Is there any evidence to identify it from Chinyu? No, at the moment, no data at specific power plants have been shared, just system-wide data. I don't think that unless they make public, and I don't know if they're going to do it or not, some data of measurements at the power plant level to say this was the protection in this power plant, in this location, this was the flag of the protection 51N or whatever the protection flag is that tripped the power plant, which that data exists. We're not going to know exactly what the culprit was, exactly where it started, and exactly which plant and which situation drove it. Gene Duran, compared to California, but given that we already we already deduced that it's an inertia issue, wouldn't it be better to compare against an existing peninsula such as Florida? No, I mean, right now the thing, Gene, is is more about not inertia, right? It's voltage, and California does have well-known challenges with voltage in the north to south and south to north, right? So there's significant studies from the 90s showing that high transfers between the regions with cheap hydro down to Southern California will cause oscillations and issues like that. The question is have we understood if that problem is going to be reversed if all of Southern California starts pushing solar up to the north? So I think that those studies are conducted in very detailed way by WEC and by CAISO, and that's why they have the regulations that they have, right? Your examples are larger systems. Well, in a way, Gene, this is again coming back to your point. We compared the span and the size of WEC with respect to all of Europe, and actually the distance between San Diego and Seattle, where you have Bonneville Power and all of these hydros, not that dissimilar from the distance between Spain and the Balkans and so on, where there's a lot of hydro and a lot of the new grid elements that have been interconnected to the European region. So I think it's going to be an interesting question over time about how do these massive interconnections can be more subject or not to oscillations, given the local grid regulations in some of the countries, right? Mustafa, good to hear from you. I think for your point about the excitation of synchronous machines, are you posing that the cost of the N-1 and 2 trips that's unlikely to do to excitations is the one? No, the point about the under excitation is that, first of all, there were already cases of under excitation protection strips because the units were driven too close to the limit. That's what's what happened with the nuclear power plant. So I don't want to make the case that that was the reason for the N-1 or 2 trips. I'm saying that some of the oscillatory behavior of the second oscillation and some of the challenges keeping the system stable get more tricky if you bring synchronous generators to operate consistently under excited and also underloaded in the active power side. So if you have to bring a lot of these units and operate them close to the technical minimum and also heavy under excitation, you risk triggering some of these situations, which could be protections like the nuclear power plant or triggering oscillations. So that's what's my point. I don't think that we have enough data, again, as I said in my previous answer, unless they actually release data to know exactly which protection scheme triggered at the power plants. We're not going to know with certainty if it was an overvoltage, it was an under excitation. The only one that we know was the report about the nuclear power plant in January, which tripped for the under excitation protection. And to Mustafa's point, this is why one of the yellow blocks of informed opinions was placed on this about what was the operator doing to control the voltage. Because in the case of January, the report says that the nuclear power plant was disconnected from automatic voltage control and it was manual control consuming reactive power, and the trip of under excitation happened when they switched back the nuclear power plant from manual to automatic control. So there's certain questions that we don't know what to answer, we don't know the answers to, but definitely they're important for the conversation. Let's see. We have a question from, I'm just gonna browse around because we have about 2 minutes, we have to finish. Julieta, how much the diffusion and motor DRs might have caused a voltage rise? We don't know, right? Again, it's the hypothesis is that if you have all of this excess power being into the grid already, the grid is underloaded from the bulk power plants, then the local distribution feeders that would be consuming reactive power will be actually provided in some way reactive power and get unloaded as well, thanks to the distributed generation. So there's not enough data provided so far to be able to answer in detail what the actual impact, right? I think that unless they release data about voltage measurements in the distribution feeders themselves that were tripped at the time, we can answer that question in more detail. Again, let me just try to grab one more. From True, would greater interconnection to the rest of Europe would have helped? Do you have any recommendation what the operator should have done in this respect to disconnected from France? That's hard to tell because yes, they could have evacuated more power into France, but remember that one of the challenges that happened, and I think this is an important question from True, as soon as they saw the oscillation, they reduced the export to France, right? It meant that locally to the Iberian system, now you have more excess active power as well. So in a way, the counterintuitive thing is like, yeah, having more interconnection with France could have evacuated more reactive power, more active power into France, doesn't resolve the reactive power. But I'm going to take your question as an advantage to mention that one of the things that could have worsened significantly the voltage problem was precisely reducing the interconnection to France, because it just created more excess generation, now not only reactive power, but also active power on the Iberian side. So I think that sets it. I'm sorry that I couldn't answer all of the questions, but thank you very much for attending.